Okay, so we are slowly approaching the last sessions, and so this session is about processing large rasters using tiling and parallelization. So there will be lots of computer science. So let me just start with something exciting. So to show you, this is one of the computers I'm computing on. It's a nice server. It has 80 threads and 400 gig RAM. So it's not as fancy as Madeleine's server from yesterday with 1 terabyte of RAM, but it's comparable. And it has this nice Xeon gold chips. So what I do here is I have a project where I will fit ensemble machine learning model. So I fit separately. And once I finish fitting the model, then I want to map some 15 variables. I want to go and map them. And so I want to map it for basically whole of Africa. And so we made this tiling system. As you see here, there's a tiling system. And so we tile all the data into little chunks so they can be read in the RAM. And then we make a code. We make a code that can be run in parallel. Basically, we have a function to predict per tile. And then I can source all that. So I just want to show you that. So when I source it, it will go and make the predictions for every tile. So it goes tile by tile, and it goes in parallel. So that's a real life example. And as you see, it takes some time. It has to initiate so it creates a 24 independent processes. So you need some time to initiate, then exports all these objects. It has to export snowfall. At the moment, you see still there's only a few threads running. So I slowly initiate it. So you see, this is all like a real life example. So don't think there's an error or anything. It's just, it takes time when the objects are large. You see how the RAM gets filled in. So it used to be 24 gig. Now it's already 27. So it gets slowly filled in. And then eventually once it, basically what it does, the snowfall sends the models and sends all the functions to each of the threads, and just passing this thing, passing it to different workers, it takes time. So it will take a bit, maybe like 1 or 2 minutes. So we'll wait for that. And then once it passes all the objects, I will be able to compute. And then we should be able to follow results as they appear. Let me open that already here. So if I look at the inside the folder where I put all the tiles, this is something about 11,000 tiles. So it's also sometimes cumbersome when you have like 100,000 folders. It's a cumbersome just to manage that visually. I will do it with the command line. Now I'm doing it visually, but it wouldn't be a good idea to open. Yes, there's a question. Yes, I shared that table to all of you using that email I have during registration. But if it doesn't match your Google account, so then just make a request. And then I just have to click, and then it should work. Okay, so now you see the exports just finished, and now we're doing computing. And now you see we are basically, because I can use only 24 threads because of the RAM problems, but I'm computing now in parallel, semi-parallel. So it will do about 98% of time is parallel, and only when it loads the new tiles, then it's not parallel. So you see, I'm computing, and I can see how the tiles pop up. So I can see here if I refresh this, I will get the most recent tiles. So you see now this is the first 20 tiles. They just popped up. So you see we compute, and I can see the files showing up in the folder. And so you see that's the files that just produced, and I can drop that. So that's the soil organic carbon, for example. I can drop that tile. Let me see here. So that's the soil organic carbon, and I can see the output here just for some random tile. So that's somewhere on the in Algeria. So I can see these predictions just for that tile. And so that's this computing with large rasters using R and using tiling parallelization. This is more or less what they want to teach you, and it's very powerful. Now I will kill this process because you know I just did it for a demo. I don't really need that. So if I want to kill it, I have to go here, and I have to first do interrupt. And then I have to stop the cluster and do the garbage collector. And I can see that the process really did stop. You see, it stopped, and it's slowly the RAM is going down, so it will it should clean up the RAM also, and then I can come back and run it again. So this is doing really computing with R with the super large data. We're doing whole of Africa 30 meter. So when you do the whole of Africa 30 meter, images are like 250,000 by 280,000 pixels. So they're huge. They are like 20 gigabytes on the, but they can be open. You can open them easily because we use Cloud-Optimized GeoTIFF. So there's another example here. I show you a machine. So that's the Cloud-Optimized GeoTIFF. And so when you prepare the GeoTIFFs, if you do it properly, this is super fast. This is whole of Europe 30 meter, and it's running on my laptop here, but it works super fast. It's magical, right? It's, you know, when you think about it, it's about 3 gigabytes of data, but we are somewhere here. So we can zoom in very quickly. And so how come it works so fast? Well, Cloud-Optimized GeoTIFF. So if you look here, it has the pyramids. The pyramids are produced, not the last pyramid, they're not so important, but these ones. So it has all the pyramids. It has the tiling, and it has also, it's compressed internally. So it has tiling, compression, and pyramids. And that's why we had this discussion with the Cloud-Optimized GeoTIFF, whether that's a database or not. For me, it has properties of a database. Edzer said, well, you cannot subset it easily. You can actually with GDAL command. Yeah, so it's a bit discussion. So remember, Cloud-Optimized GeoTIFF, we're going to talk about this, is the way to get the raster data working. This is a 3 million. Yes, Cloud-Optimized GeoTIFF, it means all the original data, it's the same. There's no difference. It has only, and that's the beauty of TIFF format, because TIFF format, it has the data inside, and it has this, header as a part of the file where you can fill in things. And so what you fill in, for example, is pyramids, tiling, etc. And so there's no, you don't lose anything with Cloud-Optimized GeoTIFF. It's just the file is usually bigger. The file, so if you take the original file and you convert to Cloud-Optimized GeoTIFF, it will be about 5% bigger, 10% bigger, depending how many of these pyramids you want to build. But it has all the same properties. There's no change. The problem is if you clip it. If you clip it or if you change it, you lose the Cloud-Optimized GeoTIFF. Only Cloud-Optimized GeoTIFF is ready to work fast to serve. For the web systems, you know, so like when you, a QGIS, for example, is basically it's use this web principles. I mean, QGIS, you only visualize, for example, this image here and in this resolution, you know, you don't have to load all the data from all the, so the QGIS automatically will clip and visualize only things that you need at the resolution you need. That's why it's fast, right? I mean, it's really amazingly fast, you know, it's just like split of a second, and the image is the 2 gigabyte. Yeah, so that was the Cloud-Optimized. So I start first with a demo. But let me talk about a bit theory also. So what I will do is today talk about like what I showed you to make your own function in R, then use the snowfall, and then run compute something, you know, using large data, but using it through tiling and parallelization. And you know, like Google Earth Engine, all this big system, they're all based on like some kind of a tiling, maybe more sophisticated than what I do, but the principle is the same. You know, you compute by copying the same process and sending it to many threads. And to do that, you need to be able to split the data somehow. So I will also talk a bit about also the packages that are useful for reading large data sets and processing large data, like doing a spatial overlay. What do you use to do spatial overlay, let's say? When you have the points and you have a layer and you need to overlay. So what do you usually use? Do you still use SP or do you use raster? Which one do you use? Mainly raster, right? So there's a new package, Terra, and it's much faster than raster. There's still improvements there, so I will show you that also. And then also you can do, you can also overlay using GDAL, for example. You can get this GDAL location info, and if you run it on a Cloud-Optimized GeoTIFF, it also goes very fast. So there's a different ways to do this. And then I will show you one example. I have a little tutorial on GitHub. So I will run with you step by step, and you can repeat what I do. So run the tutorial to see, to get the, to compute the land cover change. So we have two land cover maps of 2 periods. And what we want to find the pixels where there's a change in land cover. Basically, it's a simple operation. And, but we need to run it with the large rasters, let's say. And it wouldn't be possible to load all the rasters into RAM, so it's impossible. So then we have to do we make a tiling system, and then we run the operation per tile. And then I will also summarize a bit, giving you some general tips, you know, how to work with large data. So yes, the large data, there are the 3 things they say about large data. It's about the data can be large in sense of volume. Then it can be large because it just requires it's a long reading, writing, or computing time. And also data can be, you could have let's say some coarse data, but you have many variables, so millions of variables, and then it becomes also large data. So these are the 3 elements that make the data large. And as you see in last 10 years, you know, the data sizes, they really exploded. I mean, today, just with this Sentinel satellite Landsat, you get like petabytes of data on a daily basis almost. So the data sizes, they exploded. And we still have the same computers, you know, more or less. We get a bit better computers, but many of us, we have the same computers for 5 years. So you have this problem in the gap that you have a bigger and bigger data set. While the internet and all these other things, they grow a bit slower. Okay, so when you do any analysis, you know, when you start in R, usually we call this a development phase. Development phase is different than production phase, because in development phase, you take a little chunk of data and you really want to master. You want to master all the analysis you do. So whether in last block I did a spatial prediction or spatial integration, so I take a little chunk of data and then I really test all the things, and I want to master how I do the predictions and things. And that's what I call development. But then when you go to production, so you say, okay, now we have to do this for whole of Switzerland at 10 meter, or we have to do for all of Europe at 30 meter, or for all of world, I don't know. Then it's a really different ball game, and you have to plan. Then you don't just go, okay, now I'm going to open an R session and I'm going to compute. You have to make about 3 times more code. So it's a much more coding, and you have to do a really good computer science. So you have to think, for example, what Giuseppe was explaining, you know, like really think what is the best way to run the processing with using your computer to maximum. So it's really maximizing all your hardware, use of hardware. So I show you that plot where I have all of the cores I use, I have a 80 thread machine, and I use all of the cores and I use all of the RAM. So it means nothing's left, and that means it's a fully optimized system. The only assumption that, the only wrong assumption could be that my computing, even though I use all the cores, but my computing is inefficient, you know, but that's a different issue. But let's say you have to program in a way that you, you know, program with the big data, you have different types of functions and you do things a bit differently. So it's really different type of game. The first time we started doing any parallelization was back in 2013, 2014. And that was my first contact with the snowfall package. And it actually is my colleague Milan Kilibarda, who's unfortunately was supposed to also come, but couldn't come because of pandemic. So he started first looking at this snowfall and running this parallelization on workstations. There was not servers then. Yeah, it was the first thing was a snowfall. And interestingly now, it's almost 7 years after, we still use snowfall, more or less. So snowfall is a good package. Although now there's a high interest in using future package because it's, of course, it's more extensive and it's more and more groups use it. It has more flexibility in deploying computing on various systems. But I still use, as I showed you in this example here, I was still using basically snowfall in the back. So this one. And so I would just use that code, snowfall, basically. I think it's nice about snowfall that you literally, you see what you're doing, how you're controlling the system. So you initiate it, you say, I want 24 parallel processes. Then you export objects only that you need. You export only packages that you need. So this is not a normal library. This is a snowfall library. So snowfall library, it means it will load that library in all of the 24 processes. And then you basically run the apply function, which is called SF snowfall cluster apply. And it has this LB. And LB means if one process, if you have 20 processes in parallel, and if one process is finished, then it takes from the next 20 pile. So you don't have any losses. So it's very efficient, right? It sounds like a very cryptic. I mean, it's very cryptic, but when you split it, you understand it. Like SF is snowfall, a cluster apply. It means you apply on all cores. And then LB means as soon as you finish one process, you take from the other group. So let's say if the groups are like 20 by 20, and so you start the first 20, and from the first 20, within 1 minute, there are 4 threads left open. Then he takes from the next group, next 4, and fills them in. Okay, so it's very efficient. So it means it's in a groups of 20, but or in this case 24. But there's no waiting time. There's no waiting time. If I run this, it will continuously use all the cores to do mapping. And then once you're done with the snowfall, you do snowfall stop. And that means it will terminate all these processes that it initiated with the SF in it. So that's the snowfall. So surprisingly enough, we're still using snowfall. And we started back in 2013. Then my first time when I had a project that I had to deliver within 3-4 months. So we had to compute a 30-meter resolution for all of the world mangroves. What is the soil carbon? And I knew that, okay, I need to do parallelization. And we did it very efficiently in the end. It was, when I finish all the coding, the computing will last for like 6 hours. So it was very efficient, but I had already then, I would use bigger servers. But I did really good coding. So I even separated the scales. And so we ran the 30-meter resolution full of mangroves. It's about, I think about 2,000 tiles, 30 meter. And we computed all the stuff in parallel. And then when we produced the tile, it was just perfect. There was no problems. So that was another one. And then 3 years ago, I tried also really different tiling methods with different resolutions, global data. And so we did this potential natural vegetation. Also, we had the tiling system for whole world with about 20,000 tiles. And so then we will run that also in parallel. So lots of my daily work, it's just looking at this this server here. That's my best friend. My wife is sometimes a bit jealous, but you know, it's a good, as I said, it's a good server, and it can make you, you know, produce a large amounts of data. And if you know how to program and if you use all the RAM, it's a good feeling. And it's a good feeling that it's all open source, and I'm using R, so I can use all the cutting edge statistical methods and algorithms. But yes, so most of my day looks like this, lots of tiling, and these are all the steps. You see, these all the steps run in parallel. This is processing with big data. I cannot just run some operation. If I want to sum up values, I need to make all this code. It's 3 times more code. I have to make a code to parallelize, then to close a session, and then to bind everything together again. I also tend to separate making the functions and doing the computing. So everything you put in functions. Any process that you can automate, that you know what needs to be done, you put in functions. So here in this project, I had about 20 functions. And these are all kind of utility functions. They help me create something quickly. So this function is, for example, to create Cloud-Optimized GeoTIFF. So this is a function before the Cloud-Optimized GeoTIFF driver existed. This function helps me create a Cloud-Optimized GeoTIFF, and it works with any type of data. And I had to tweak it a bit, fine tune it, because I want it to also very fast. And then once I get it, then I just run it, and I can produce from you know, 10,000 or 50,000 tiles. I create a Cloud-Optimized GeoTIFF. So I create all these functions, and then in this code I do the production, and that means here I do model fitting, overlay, also everything in parallel. Overlay in parallel, model fitting in parallel, prediction in parallel, making the sentinel, making the mosaics in parallel, everything in parallel. And then you see the code is, yeah, it's much longer. I'm here now. Let me see. So this is something like, I have about 400 lines of code to do production, and I have here maybe some 800 lines of code, 700 lines of code with functions. So I'm now about, so that's about 1,500 lines of code to do that project. Yes. So that's this Africa. You see, we split it into about 9,000 tiles, and we use the 60-kilometer tiles, the one I showed you. And this also choice of how big is the tiling system. So it's also, it's horrible sometimes. I had the one project, I pick up the tile size a bit too high. So when I created all the data in tiles, because I have to clip all the data to tiles, then I realized that it blows up the RAM. It was too big. So I have to throw everything away, and I have to retile again. So I create a smaller tile. So everything you do, you know, it's a really computing engineering when you come to big data. So you have to really carefully check everything. There was also, it's very silly. So we created this first tiling system. I used a 50 by 50 kilometer. This one is a 60 by 60. But I used 50 by 50, and we started doing a sentinel data. And then in one stage, we pick up a 30-meter resolution. But the 30-meter resolution, when you put in the 50 by 50 kilometer, you get a decimal point. So you have to split the pixels. So it's a funny thing, but it's a pain. So we had to remake the tiling system. And luckily, I have my own function for tiling, so that wasn't so much work. But I had to throw away the tiling and then remake the tiling system that I can fit in 30-meter pixels. Because if I have 50 and 30, it just doesn't fit. It's 1.76 something, I don't know. So yeah, that's also another thing about tiling. This tiling function I made, get spatial tiles and tile. I made it also with overlap. And overlap is very important. This example where we computed the topographic wetness index, but this one looks in the neighborhood. It searches in the neighborhood and then calculates a flow. So if I will run it by tile, then it will have artifacts. So all the lines will be visible. Yeah, so it's unusable. So what I do, I create a 60% overlap. So I create a tiling system where the tiles, they overlap. and then I compute these hydrological indices, and then I bind it together, but I clip only the center. And magic, so I show you when I do that, then the tiling system looks something like, the output looks something like this. And you will see that you don't see any single line. Let me open it. So here's this topographic vendors index. So if I open it, you will see that there's no problem with the. Oh, sorry, this was the downscaled. I need to put this one. Yeah, it's actually the same. So if I look at this, you don't see any blocks, right? There's no effect of the proximity. Do you see this? There's no effect. So that's what, because I put the overlap, and this overlap, I had to run it few times. So for few tiles, I have to see how much is overlap. Sometimes you need like 100% overlap. So basically you take 3 by 3 tiles, and you compute everything, but you take only the values from the center. And then you move it and you compute it. It's like a moving filter. But here I did a 60%, and after we computed, bingo, fantastic result. There was no problem, and we could use that. And of course, it comes very important for soil mapping. So we could use that to do. And you see, there's absolutely no visible, this, when you have the blocks, you don't see any problems, no artifacts. Okay, so you have this, as I said, the data. When you organize the data, if you do everything properly, you create this Cloud-Optimized GeoTIFF, and then this is the one for Europe. That's our project GeoHarmonizer. So we created the land mask of Europe, basically, and we put only the land mask that we're interested in mapping. And then here's this tiling system. Immediately we make a tiling system. And so that looks like this. This is also a 30-kilometer tiling system. So we have 1,000 by 1,000 pixels. So 1 million pixels, a nice round number. And let me put this just so you see. So that looks like this. And so now I could read any individual tile. I could see which are the pixel coordinates. So if I look here, then I can get the pixel coordinates. And so, you know, with the images, you have two coordinate systems, right? You have a one coordinate system, which is the XY coordinates, so the projection coordinates, and you have so-called image coordinates. And image coordinates, they're actually measured from the beginning of the image. It's on the upper left corner. This is the first pixel in upper left corner. Has the coordinates 1, 1. So these are the image coordinates. And then in the right lower corner is the last pixel. And this pixel has the coordinates exactly the size of the image. Yeah, so these are called pixel coordinates. So if I want to read that tile that you see here, then I can use a GDAL, and I can say I want to use a GDAL. I want to read this from this image, but I only read starting from this upper and lower coordinate, and I read only 1,000 by 1,000, so the dimensions are 1,000 by 1,000. So I will have to start reading from the 7,000. So to read this image, so I will start from here. I have to start reading the pixel number 77,000. 99,000x, and then in Y direction 77,000. So that's this pixel here. And then I read 1,000 pixels this way, 1,000 pixels this way. and then in GDAL, I get that information inside. I will do a demo after I finish all the theory. I will do a demo so you will get an idea how this works. But so that's how you deal with when the data set is large. The data set, if I look on my computer, so here's the data set. You see it's about 1.2 gigabyte. So if I go now, I want to read it in a RAM, I crash the computer. Yeah, so that wouldn't work. But I could do, what I could do is if I use a raster package, I just want to find out about it. So about this image. So what I could do is I could do, say, a raster. And I know it's a data EU3. And that's the file. So if I do this, so if I do this, this doesn't, so raster package is smart, so it knows it's huge image. So only if it's a small data set, if it's less than, I don't know, 300 by 300 pixels something, then it reads it into RAM. But otherwise, it just makes a header. So we only see what are the properties of this data set. So there's no data, just the structure, just the geometry, coordinate system, etc. So I can see it's this European coordinate system. It's called European reference, terrestrial reference system, something. So that's this European coordinate system. As they also mentioned it, that expectations that we make all the data same, exactly matching that coordinate system. Okay, so when you speak about large data, so there are three, as far as I know, at least from my point of view, there are really only three ways you can deal with this. So you can use a software that handles large data. And so that software internally, it's optimized. It recognizes if the data is big. And then it does parallelization internally. And then the second option is that you make your own functions. And then the third way is to, instead of you doing it locally, you do it somewhere, you outsource it. So you use just Google Earth Engine because they have it solved. Okay, so there are the three options. Either you use a software that will internally do parallelization and everything, or you make your own functions. And these first two I'm talking about locally on your machine. And then the third one is just outsource computing. And one way to outsource, as you saw, it's, for example, Google Earth Engine, and to use some cloud service, Amazon service, etc. Then you don't need any local copy. You just need to code. You need to code in that system, in that infrastructure. But sometimes that can be uncumbersome, and many companies, they don't really provide any support. It's not friendly, you know, like Amazon Web Services. You have to be really good programmer. I mean, there's a lot of things you can do, but you have to like figure out many things just by running code. It's a very little graphical user interface to do things. And Google Earth Engine, you saw, it's even worse. You know, people, there are many people. There's about 60,000 people, as far as I know, they use Google Earth Engine almost every day. But if you go to Google Earth Engine, it's JavaScript. That's it. There's nothing. It's just JavaScript. If you don't know it, it's bye-bye. So it's even worse. It's even more, you know, it demands directly that you are a good programmer, and not even programmer some language like Python or R, but JavaScript. Okay, what can go wrong? So when you do computing with large data, so because many processes are sequential. So like I showed you, this thing I'm doing computing, I make 1,000 lines of code, 1,500 lines of code. I have different steps and I have to parallelize every step. But in order to finish the project, I can have only one step that I cannot parallelize or that doesn't work. And I can fail, you understand? I won't be able to finish. Because if it's only one step, it doesn't allow me to get to point A to point B. And it's been a headache really for me a long time. I will do like 80%, 90% of stuff, I solve it. It's the fastest possible. and then just the one thing, you know, just sometimes just transferring the data or doing just a spatial overlay, it takes 6 hours. And then my process, and I just look at the worst thing, the worst image you can imagine is if I look, for example, at this server, and so once you get the most serious computer, it's a pressure, absolutely pressure, because if I do now some computing and I use only one thread, it makes you want to cry. You know, it will be like you get a Ferrari and you can only drive like 20 kilometers per hour. So it's very difficult. So you need to make sure that when you do the coding, that you can parallelize everything basically, and that you can do everything in parallel. And I keep on digging. Then I keep on digging when I had the problem like just writing R images or something. For a long time, I was like, I will wait like 1 hour to put that image on the disk. But then in between, I find some functions you can do in parallel. You write image, R objects, etc. Okay, so that's the one thing that's very painful. Then if you do this parallelization, sometimes it creates an illusion that you are using your server to full capacity, but actually there are hidden problems, and you can maybe you in you use some wrong function, and then you leave it running for 1 day computing, and you come next day and you notice that okay, it computed everything, but it was some error. There was a small error. So I had problems with rounding numbers, simple stuff. You know, I would take a wrong function to round the numbers, and my thousandth line of code, it's all fine. It's just that line where I round the numbers, I messed up. I have to recompute everything. I also saw when I had students, I saw a couple of times some of my students, they take some machine learning and they let it running. And I asked them, what are you doing? They say, I'm fitting a model. And I said, well, when did you start? And one guy once said a week ago. Yes, and I said, well, how long does it take? I don't know, I'm still waiting. So yeah, never do that. So computing engineering, never start any process that you don't know when it's going to finish. This is not fishing, you know, it's not like I go fishing, so maybe some fish will, you know, there will be fish or maybe not. So you have to really plan. So how do you solve that problem? Who could help me? How do you do properly computing engineering? What's the proper strategy? Matej, come on. So you take a huge, large data set and you subset it to 1%. Let's say if you have a regression matrix, you have to do some random forest and you have millions of rows and thousands of covariates. Then you subset it to 1% and you just, okay, fit. And you say, oh, why it takes 1 minute. Okay, the next thing, what do you do next? I usually do that. Yes, if you do like, if you increase like 1%, maybe 2%, 5%, and you only see that the time grows probably exponentially. And these 3 numbers allows you to fit a function. And you fit it in hours. So you fit, okay, I get this 6 pairs of numbers, 3 pairs of numbers, and you fit a little function. And then you say, okay, what if I do 100%? And it says it will take you 12 hours. Yes? So that's a way to plan computing. But never, please, never do that. Leave the computer something in R without knowing when is it going to stop. I don't have to know in a second. But I really, seriously, I had a student and I asked him, when did you start computing? And he says, a week ago. I said, you could wait for 1 million years maybe. It's possible if you don't know how long it takes. There are many things you can make a code. I can make a code that runs for 1 million years without stopping. So you have to do that. I also had a lot of problems with the zombie processes. When you do parallelization, they're called so-called zombie processes. Madeleine, you have experience with that? Yes, it's horrible. And sometimes the only way the only solution is the restart or like cleaning up everything. So what you have in what's very nice in when you work with Linux. So let's say if I'm here, so what I can do, I have now this RStudio in the back, but I can also do something like this sudo partial kill. And so that will search anything with the word and kill all the processes in the system that are partially matching. So it's called partial kill. And so I'm looking for Microsoft because I use Microsoft R. So if I run this, it asks me for my password because it's a sudo. So if I run, oh, wrong password. So if I run this, it will kill all the Microsoft processes. And you see here, you will see that this process was basically killed. Even though I see it, I will need to do a restart and then get back Microsoft R running. So this is the, sometimes this zombie process can be really nasty and there's no way to see it. And then also sometimes many times you run out of RAM. When you run things on Ubuntu, if you run out of RAM, usually Ubuntu will kill the processes, but sometimes it doesn't. I had a few times I did some double parallelization and I loaded with all the RAM, and also I flooded my disk. So my disk ran out of space and my RAM ran out of space. And I couldn't connect to the computer anymore. And it was running infinite loop. Okay, so I really messed it up. I was almost proud of myself. And so the guys at the company told me that they had to physically reset the computer. They said, we rarely do that, like once in 10,000 times. So they had to physically, there was no way to connect or remotely reset. So I was really proud of myself. So if you flood your computer, so you run out of this space and you take all the RAM and you run some infinite loop operation and you do a double parallelization, then you have a good chance to really destroy the machine. But so all these things can go wrong. If they don't go wrong, then you get something like this. As I said, that's the usual, my workday. Any project we do, we parallelize computing, we have our own machines. We are investing in our own infrastructure. We also use both Amazon, Google and OVH and a couple of other companies we use to do computing, but we do a lot of computing in-house. And so if you do everything properly, then this is the happy image. It's the happy image you get. So it's a fully optimized for computing. Maybe here I don't use all of the RAM, but it's also good to use all of the RAM. So ideally you should use all of the RAM and all of the cores. So the lessons I learned, so you see planning. So before you jump into computing with the large data, you have to plan. Eventually, there's no way you can avoid investing in the hardware. If you want to reduce the amount of computing from 1 day to 1 hour, it's possible, no problem, but you have to go from, I don't know, 8 threads to 80 threads. And so that's sometimes unavoidable. Obviously, if you work with large data, you need storage. This specific server I showed you here also has, let me see. So this specific server, it has a 4 terabyte SSD drive. So it's this one, PCI. And so it has also so this disk is 3.8 terabytes, so almost 4 terabyte drive. So when you combine good chips, a lot of RAM and the SSD, you do really amazing projects. So one more time, this server, it's about the value, it's about 10,000, just to give you an idea. Now the prices went a bit lower. Then when you do the tiling, I showed you the examples where when you do tiling, sometimes tiling you have to do with overlap. Sometimes you have to do hierarchical tiling. And then when you do a parallelization, it takes a bit more time coding, you know, like when you do small data and big data. So the difference is with small data, I have a process that I take from somebody's book or from some package, and I just run that process. When I have a big data, I have to make 2 times more code around that process that makes sure that this process is computed in an optimized way. And so the only really satisfaction here is once you have, as I said, once you have something like this, then you know that your computing with large data is ready, because you see that there's no threads being left out. You use your hardware to maximum. Then also making scalable code. What does it mean, scalable code? So scalable code is you make a function. And this function, if possible, it will look for the properties of the system itself. So, you know, there are functions in R that will look how many threads I have on my computer. So there's this function here from the parallel package. So I don't have to go and check that. It tells me how many threads I have. I have 12 cores. So on this machine here, if I look at task manager, I can see that indeed I have 12 chips. Yes, so I have 12 chips, you see? And I don't put that number in the function. What I will make a function, I don't know, some test function, and then I will say CPU is, and then I will put this stuff. So then when I deploy that function on some other computing infrastructure, it will automatically use 80. Okay, so it means that everything I program, it's easily scalable. So if I move that function to another system, it will also run and use all the hardware. So that means programming in a scalable way. And scalability is very important because it saves you a lot of time. And so basically, once you make a good function, then it should work on different infrastructures. And then the only way to do that is to understand in R, how do you query infrastructure, and how do you query, and how you can even estimate how much time you need and how do you have to split the data. So it's all possible, but you have to put it in a function. Okay, so these are the main lessons I learned. And then you saw the presentation by Leandro. It's also good. It's very good, even though you can do lots of things offline on your locally in your system. But it's a good also to learn how the things can compare, how the things done in some massive infrastructure, and what is the logic and how the things work. And so please look at that slides also once you go back. Look at that slides. Okay, now when you read the data, so I spend, I mean, I've been programming almost 15 years in R, and so I had lots of problems with the CSV files going like a few gigabytes, you know, CSV files. And then I find, for example, that there is a data table has a fast read. It's amazing. It's really amazing. It will read literally in 20 seconds, reads like 1 million rows, or like a 5 seconds. And so, but the data table package is really famous. It has many solutions, and I don't know how they do it, but they managed to get that operation running very efficiently. So if you remember, if you read a tabular data, which is large, which can be just a text file or CSV, you can read it very efficiently with the fread. Then if you do the shape files today, the fastest way to read shape files is the SF package. And then if you work with the large rasters, then I recommend using the Terra package. Even though there's a stars package, you saw the GDAL cubes, but I still think the Terra package it's the most comprehensive, and you can very quickly start going and doing things. But as I said, the GDAL cubes and stars, they have this time dimension and things a bit organized, more complex. So if you do have a time series, then probably you can use the stars package. But if you just have the layers and you need to do overlay, then use the Terra package. who does the overlay with Terra, spatial overlay, points and rasters. So go and test it. Take same, so you can always do like a, so you take the system time. So this one is allows you to, when you do some process, allows you to see how long time it takes. So let's say if I do something like this, so that will print out how much time this operation took. So this took 3 seconds. And so you could also like do overlay. And so you take the, if you compare raster package and Terra package, you see that it's an order of magnitude faster because it's been recompiled in C++. And it's very efficient. And also, so you could go and check that and test it. In a raster package, you can also do things in parallel. This is some simple computing, I think, deriving a NDVI or something, just taking 2 images and then deriving NDVI. So it can be combined with a do parallel on for each. So they are basically parallelization packages. So they can be nicely combined. So you can take a large raster and it will run it in parallel and without loading into memory the whole images. So that's also possible. And there's a nice tutorial here that I share with you. Now the GDAL warp, the new GDAL. So first thing about GDAL 3.1, very important that you can make a cloud-optimized GeoTIFF in a single line. I used to have to make my own function. I would spend 1 week trying to figure out how to make the cloud-optimized GeoTIFF because there's no simple solutions and guidelines. Now they tell me, okay, now there's a driver. So you will just say in the same line, you do GDAL translate, and you say, I want this GeoTIFF to build the pyramids, make the tiling system, and put the compression. And then you get the cloud-optimized GeoTIFF. But I used to have to do it by hand. Also, GDAL warp is one of the most used commands in GIS at all. And you see it has also this multi option. So it will, you can say, I want to use all CPUs. So when you do reprojection, resampling, cropping, so that's all GDAL warp, right? Cropping, reprojecting, translating, subsetting, extracting bands, everything. You can do them, you can do it in parallel. So it is efficient. And that's why Giuseppe uses also from command line, just GDAL. Okay, so also when it comes to the data, so different type of data have different formats which are more flexible for larger data sets. So if you have a large tabular point data, suggestions to use PostGIS, it's the fastest to subset, query, do operations. And you can use them also from R. You install PostGIS on your computer, then you put the data in PostGIS, and then you use the R command to query and get the PostGIS. Then if you work with the vector data, line of polygon data, recently they recommend using this flat GeoBuff, but as you see, I created that for this point data. This data, for example, now it goes very slow. It's a very slow loading, right? So it loads very slow, these points. So the idea is that if I would use, like this is impossible to look, right? I mean, it takes 1 minute to load the points. It's 3 million points. And so what Johannes is now looking at, taking that, so I managed to export that data into the, so here. So I exported to the cloud, to the flat GeoBuff, FGB. So I have a geo package is 900 megabytes, and this one is 1.3, so it's a bit bigger. But if I want to drag and drop it, I think it's still not supported. It's not supported in the current QGIS, because I think this QGIS uses the old GDAL. So it hasn't, they didn't recompile with the new GDAL, the 3.1. This is really the newest GDAL 3.1. So Johannes, you're going to test if you could do, are you testing now? But yeah, GDAL on Unix is a pain. On Windows, you get it very quickly, but it's a pain on Unix, yeah. Because you have Ubuntu probably, no? You have what? Windows. But Windows you install. I have the. You see, this is Windows, and I have system. This is 3.12. Yeah, I just don't have time to make the code. That's the problem. So yeah. So yeah, so my laptop is now sweating because it's trying to plot all these points. Then you have the Cloud-Optimized GeoTIFF. For how many of you already use Cloud-Optimized GeoTIFF? Okay, Danius, of course. So yeah, if you don't have, like, you know, if you have a GeoTIFF 20 megabyte, you don't need it. But as soon as you move to gigabyte and few gigabytes, if you don't use Cloud-Optimized GeoTIFF, it's, forget it. You cannot see it. You cannot look at it. Understand? If you open it, you won't be able to see anything. But as soon as you build in the Cloud-Optimized GeoTIFF, then what happens is, even on this little laptop, you see I can zoom to 30-meter resolution data, and it will be in a split of a second. And how is that possible? It's possible because it just loads these pyramids and the tiles, you know, that you need. Okay, this is the flat GeoBuff. Somebody did actually the person that made the driver. They did comparison. You see, it will be much faster reading, writing. Not even comparable to like shapefile or anything. So it will be usually about 30 to 40% faster. So that's very exciting. But yeah, we have to see how does it work. So when you do the overlay, if you want to get it done fast, then you use this function, Terra extract. So you have to specify your TIFF on your computer. You don't have to load it in memory. And then you have the XY coordinates. You have to say which projection system are there. And that's it. And you do that, and it will be the fastest possible overlay. And you don't have to load rasters into memory. And you can go beyond that. You can make code to run this in parallel. And so you do something like this. So you do something like this. So you see this code, I'm running parallel. I'm running multi-core lapply, MC lapply, and I will take a list of GeoTIFFs, and then I say use all the cores. So in one line, I do overlay in parallel. So you say MC lapply, and you say this is the list of TIFFs I have, and then take each TIFF and overlay these points. And as the output I get in parallel, I get all the values. And you can combine it also with the Terra package. So you can do fast overlay and in parallel. And how much time you save can be 100 times, depending how many threads you have, of course, but it could be a really big difference. Okay, so when you do the large GeoTIFF, so I made that in landmap package, you have that function to do tiling. So I made a get spatial tiles, basically based on the geometry of an object. I will tile it, and then you can create polygons from tiles, and you can then plot it, and then you can read only specific tiles. When you write objects, so R data, the effective way to exchange data is using the RDS format. Okay, it's a very effective way. It has a compression, and you can, with the RDS, you can, if you just load an image, R image, then you don't know what are the objects inside. And with the RDS, when I write RDS and I read it, I can rename the object. And usually with RDS, the best is just to write a single object. So RDS is a very efficient way to exchange data. It has a compression, and you can rename the objects. But there's a functions in, this doesn't work on Windows, but on Ubuntu, there's a nice function to do in parallel. So you write, if you have a large object, you can write in parallel. So it can be very important, because if I have a 2 GB object and I write it with one thread, it takes me 5 minutes. And if I write it with 80 threads, it's done in 5 seconds. So that's very important. And you can also read in parallel. So that's all very well done. And there is also fast save. Have you heard of fast save? If you load large objects in R, you create these large images. Yes, and then with the fast save, you can save that image in parallel. So if you have a big server, it makes also a huge difference. And these are all the functions that are available to do load fast and save fast. The only really difference is from the normal save is that it runs in parallel. That's why it's faster. SAGA GIS, it has internal parallelization. It's one of the best GIS software in the world. So anything you run, if you have a large data set, large raster, anything you need to do, like a principal components, a filter, or do raster calculation, you can use directly SAGA GIS. I use it to crunch large data sets, like whole world 100 meter and even larger. And it works no problem. It's efficient with the memory, and it's automatically parallel. You don't have to do anything. So it's so that's the scalable code. So Olaf Konrad and his team, they did very good. So if you have a new SAGA GIS, maybe one of the biggest lessons from this summer school is I have to get into SAGA GIS. And you have to use the command line. And you can use it from RStudio, as I showed you. You just use the SAGA GIS from command line. So if I go in my RStudio, I can do system, and I say SAGA command line CMD, and I'm looking for help, and I will get back some help. So here's the explanation. So I see the SAGA GIS version, and I see what examples how you do the code. And you see there has a one setting, which is this -C. So I could also limit to a single core, but by default, SAGA GIS Smart, so it takes all the cores. So if you have 1,000 cores and you need to do some operation, it will be done very quickly. GraphGIS, how many GraphGIS users? GraphGIS, one? SAGA GIS. Yes, you can use the RSAGA also package. I don't use it anymore. I prefer command line. Yes, everything. Yeah, it's just a wrapper to make maybe a bit easier, but I do everything the same with command line. So yes, Madeleine? So RSAGA CMD, yes, I see it. This one. And who's maintaining it? I didn't know, but it's great. It's great to see. Stephen Paul, yeah, great to see. So yeah, this could be maybe for you. I still use the command line. I just got used to it now. It's a pain, but you have to make a R code that converts the functions to SAGA command line. But I got used to it. Maybe this will work easier. Okay, now we go to the example. Oh, by the way, I have to close the spatial prediction competition game. No cheating. Okay, let's wait for this. Looks like Google is taking more time. I think I was just pressing this and then somebody asked me a question. I didn't check whether this went through. So yes, I don't see anybody submitting. Let's see one more time. Yes, I need to copy again all the names and then share it. Yeah, sorry about that. Maybe I shouldn't have put the end of the. Okay, let me do the example of, so we have this data set, which is the land cover time series data set. It goes from, what is it, 1998. There's a 5-year period. But so there's a data set, which there's a time series of land cover images. And so that's about 300-meter resolution. So it's about 1.4 billion pixels. So it's not something I can read in RAM. So if I read the 2 images, it's about 6 gig. Or one image is 6 gig. So this will take about 80 CPU hours to compute. So if I have 80 chips, in 1 hour it's done. You see? But I have to program it. So, so then I will look at the structure, I prepare a tiling system, then I prepare a little function, and then I run in parallel. And this is the system I showed you. That's what we use, the syntax gold chips. I have now 80 threads, not 64. And we use the SSD disk. And so that's how the function looks like. I make this function to do, to compare whether there's a change in the land cover, and then attach some value from some table with the plier package. So I combine the plier and GDAL and everything. And then I run that in parallel using the snowfall. SF cluster lapply, SF cluster apply LB, and then I run it in parallel. And then you see this, I put it per folder. And as I said, in 1 hour it's done. And then once I create all the tiles, then I create build a GDAL build virtual raster, a virtual what's it called? Virtual mosaic, sorry, virtual mosaic. And then I do GDAL warp, and then I can produce an output, and that looks like this. So that's for the whole world. So you can see we can compute all the areas where there's been a land cover change in last 15 years. So that's an example, and you can run that example from this repository I made, which is called Big Spatial Data. So this is the first example. So basically, I will point to that file. Now I take only Indonesia. I don't take the whole world. It's too much to put 3 gigabyte on the server. So I take only Indonesia. So that's about 6,000 by 6,000 pixels. So or 6,000 by 5,000 pixels, relatively small. And then I have two dates, and then I make this function. So this function will read first the first date, then the second date, second land cover. Then I will name them land cover 2000, 2015. And then I will compare if the values are the same, then there's no change. And if the values are not the same, then I attach a combined value. So going from one class to the other. and then I write that out as a GeoTIFF. Okay, so that's that function. And then I have this legend that I attach. So these are all the combinations. So if I have like 16 classes, then I have many combination of classes. So I come to about, so this is 18 classes, actually 18 classes. No, sorry, 38 classes. Then I come to something like 1,400 combinations. So you can go from forest to cropland, from cropland to cropland, cropland to cropland B. So these are these combinations. And then I make the tiling system. And then I run it all in parallel. And so that looks like, so this is this Indonesia tiled. I just use the TMAP package to plot that. And then I can run that in parallel somewhere here. Yeah, so here's the parallelization. I run it in parallel. I use all the threads on my laptop. And then I get all these tiles, and then I just combine the tiles and I create the mosaic, and then I can open that mosaic and look at the Indonesia. So that's what I want to show you. It's a very gentle introduction. And if you learn how to do this with a little example, then you should be able to run it with your own functions. So you could also use like 1,000 of rasters and use your own thing and do computing. Okay. So if you want to follow this, the best will be to take this, if you have Windows, you install the GitHub desktop, and then you go clone repository, and then you just put that URL of this repository, this one, and it will automatically clone it. Oops, sorry. So if you just clone that repository here, it will automatically clone it, and then you can open that in RStudio. So you just go open project. And I go to that Git folder where I saved it. And so here's that project. And now you can do the same thing as me. You can follow that exercise from here. And I'm looking at these deriving differences in land cover. I just have to first, I have to get all these packages maybe. So if you haven't installed the packages, this command line will go and install all the missing packages. So it looks whether you have them. If you don't have them, then it installs it. So as I said, I have this GDAL and raster, that's what I use. And so when I look at this layer, and let me open that layer now in QGIS. You know, I'm using now a relatively small image, so you will say, wow, you're parallelized, but I use it because it's just for teaching. I'm just doing it for teaching, but it looks like this. Let's see, open. So it looks something like this. So there's the tiling system. This is this land cover, the land cover image. And you see this, the tiling system will prepare. And then here if I zoom in somewhere, you can see this 300-meter resolution land cover. Yes, so I use this image, which is a bit not so big, but in reality, you can work with an image which is like 300 gigabytes, right? And then you need to tile it because there's no way you will be able to process it with R, unless you use the GDAL cubes or something. But otherwise, you need to tile it. So that's this example. And as I said, we have two land cover images, and we need to compute this change. And see, here I have it already computed. So I'm just showing you. So we have to do this. We find this pixels where there was a change in land cover, and then we attach to that change, we attach a new code, which is the old land cover and the new land cover, only to the places where we have change, right? If it's no change, we're not interested. So it's all missing value. But here we attach a new value. So it says this one is changed from the forest to banana plantation. This one is changed from this to that. Okay, so we have, if you're following me, so if you want to follow, as I said, you got the GitHub, which is in the Google Calendar. You do a checkout using the GitHub desktop or using Ubuntu. If you do the git clone, and then you get a local copy of that folder. And you see in that folder, you have, let's see. So in that folder, you have some tiled, there are some tile folders. These are like individual tiles computed. So you just see. And then you have the data folder, which has all the data used in different exercises. And the two data sets we're interested in is the Indonesia land cover 2000 and Indonesia land cover 2015. Okay, so first thing I just check, I don't load this data in memory, I just check it. And then I make this function. So let me see this function. So what does it do? If we zoom in, let's zoom in on that function. As I told you, I will read first. So here I read the, I specify the output file, output TIFF file. So let's see if we do the I. We specify some I, and so we read a single tile using the GDAL. And this is now where this image coordinates come, because when I specify offset, you see this offset, it means start reading the image from some pixel coordinate, and then read 300 pixels this way, 300 pixels this way. And that means it will just read that tile. Okay, it's a very nice thing about GDAL that you can, based on these coordinates, you can just read the data. You don't read everything in memory, but you just read it a little chunk. And then I read it here, and then I read the second land cover, and then I just rename. I rename the bands, so I have 2015. Then I make it a special pixels data frame. I dropped everything which is missing value. And then I can say, okay, all the pixels which are the same, don't do anything, just take the pixels which changed, and then attach to these pixels, so like a database operation, attach the values from this legend, the new legend, which is the 1600 entries. And this is a little, it's called a wrapper function. And you see this wrapper function as an argument. Let's see what does it says. It has the I, so which tile you're working on. It has the table, tile table, so it's a definition of tiling system. It has the output path, and it has the input images, and that's it. Okay, so it's a little wrapper function that I made that allows me to parallelize, and so I can run this function now on every tile. So that's the first. I made the function. Then the second is I created this legend, which is the combined legend. As you see, if I look in the head of this, so this is the combined legend. So I have the first land cover, the first land cover, the second land cover, and then this is the combined land cover. So first to second. And some of these combinations don't exist. Many combinations, maybe 70% don't exist. Yes? So I make these combinations, and then the next thing I do, so I already actually made it. And the next thing I do, I prepare the tiling system. So the tiling system, I will just do the GDAL info, and then I say create a tiling system. And I say I want the tiling system of 50 kilometer. So 0.5 degree, it's about 50 kilometer. And then my function tells me this is 550 tiles. If I want another tiling system, I say I want it smaller, then I just create this block X smaller, and then it creates more tiles. Or if I want a bigger tiles, so I can quickly do that. And as I said, I can do the also the control the overlap. And then I can put the ID to each of the tiles, so I get something like this. Did I do a sync somewhere? Ah, here. So I can do also the this one. And so it looks something like this. So that's the tiling system. So I have the upper left X, upper, so Y left, lower X, lower Y, and upper X and upper Y for each of the tile. And then these are the beginning of the offset. So there's the image coordinates, and this is the size. So it's a 240 by 240 pixels. So I basically can split now this 5,000, 6,000 by 5,000 pixels image. I can split it into 550 tiles. And this is my tiling system. And this tiling system I can also write into the QGIS and then open it and show it here, right? This is this tiling system. It looks like this. And you see here on the edges, look, my tiling system, when it comes to the edges, my tiling system will start from the lower left corner because it's that's how we usually think, the lower left corner. But when it comes to the edge, it creates this irregular tile. So it will fit exactly the area, right? And that's no problem for the mosaics because mosaics can be irregular. You can have irregular tiles. That's no problem. But it on the edge, because it's not exactly, it doesn't divide by the size of the tile, then you have some areas that could be small. If it's less than 2 pixels, then it skips the pixel. So if it's a less than 2 pixel size of the tiling system, then it doesn't do it. And then once I'm done with that, here I can do this plot just to see how the tiling looks like in R. And I could also do just a single eye, and it's just a single tile. I can read it into R, and then I plot it, and then you just get this little single tile, and that's the tile 124. I could find it somewhere in QGIS. So I would have to click here and put some description, or if I just search, so that's 200 somewhere, 124 says, no? So it's somewhere here. It must be somewhere here, this way. 123, so it's somewhere here, this tile, okay? And this is an example where I can read it and I can plot it. And now everything is ready, so I can go and compute it. So I can compute, except this is not going to compute if I have the tiles. So I have to remove the tiles. Let me do that. So I go to tiled, and I just delete all the tiles. Okay, so now it's empty. So now I run the snowfall. And now I look carefully in the folder. And so you see the tiles are popping up and they're being created. Yes, so they're being created. It will take maybe a few seconds. In real life, you know, it's still computing. In the real life, when you do large images, then it can take you know, hours. But now it's done. So it takes about 10 seconds to compute 550 tiles to do this. And it runs this in, on my 12 cores, it runs all in parallel, okay? But so now I have these tiles, and some of the tiles are very small. It means it's a small difference. But in general, yeah, it's very small. This one is a bit bigger difference. So let's take a look at this. If I just put this tile here, I can see where does it fall. So here's this difference. And so I can put that in the background. Maybe I put this in color. Where was it? So it looks like this. So here we have the old land cover, and these are the pixels where there's a land cover change. But it's only for that tile. And so the next thing will be, so I have these tiles, but I need to put them together. So I want to create again. So I go from an image to tiles, compute something, I get the tiles back, and then I put it together and I create again the final file. So I list all the files, and so I have 295 files. How come I don't have 550? How come I don't have 550? Well, if you look at the functions I made, I specifically made it so if there's no difference, then basically I say don't do anything. So this thing. So I look here. If there is no difference, then don't do anything. Skip it. Only make a TIFF, make a file if there is a difference, and that helps me to speed up. You understand? I don't need to create tiles that there's no difference. They're empty. So there's no need to create them at all. And it's also beautiful then with the GDAL that we can go and then say create a mosaic, and it will create mosaic. So I will say here's the temporary file, and here I create a mosaic. You see it's done very quickly. And this mosaic, even though it doesn't have the styles, when I convert that mosaic into a GeoTIFF, then I get a complete file which has no, well, it has all missing values, but it doesn't look there with no tiles. And so that's on the end, that's the result here. And so that's the whole of Indonesia. You see it's exactly the same tile. And we see for whole of Indonesia, for Kalimantan, not whole of Indonesia, we see the land cover change. So the 15-year land cover change. And now it's a single file, and I could now also convert it to Cloud-Optimized GeoTIFF, and then my project is done. You see, that's how you do with R. You take a large data set, you make a tiling system, you make a function that works per tile, you run it in parallel, and then you create it back, and then you say, project done, here's the map. Okay? So this is basically what I wanted to show you. Let me just see for the competition game, there's some problems. Let me see. Yeah, I just cannot share. Something's bugging. Something's bugging. Yeah, I'm sorry about this. Okay, well, let's see. I'll leave it on. Okay, last try. Let me see like this. Ah. Have you, those of you that need to submit the predictions, did you request access? Because I'm not getting any. You requested access because I wasn't getting any notice. That's strange. Yes. Mohammed Reza, can you approve people that want to access? Do you get a request? Usually I will get a request. Okay, so maybe you just send message to Mohammed Reza, I need an access, and send your email, and then he will add you, because you are just, I don't know, I didn't have these problems before. I'm just having problems adding people, so it just doesn't work. Okay, I go back to my lecture. So that was a very straightforward, I think, how to do tiling, then parallelization, and then how you create a virtual mosaic and you get your file back. And but the only way you can do this yourself is to start testing. So it will take you some time. But how many of you do parallelization? Okay. And how many of you work with the tiling systems? So tiling things, yes. Then you see only. So yeah, I was also, I was surprised when I wanted to do tiling, I couldn't find any function, so I made my own. So I couldn't wait, so I just made my own function. And it does work. It's a simple thing, but it helps me always move. And then also debugging, you know, if I just take one tile and I try a function, and then I see what's happening. So it really helps me, because if I test, for example, 10 tiles, then I know the method works. And then I run the parallelization. And if you don't have anything that you can clip, you know, your things and test it, then it's very difficult to see if it's a good process. Sometimes people compute everything and they say, oh, it doesn't work. It's a waste. You know, you should compute only a few tiles. You take test tiles, you compute function, and you say, okay, it works. And then you do the whole thing. Yes, that's again computing efficiency, right? The worst thing is that you compute everything and you say, oh, it doesn't work. And then oh, it doesn't work. It's just a waste of computing. With the tiles, you can be very fast. You get it in a few seconds. And then if you have 10,000 tiles, you test 10 tiles. And if it works, then you run on 10,000 tiles. So Mohammed Reza, please, can you add the people that need to fill in? Sorry? Okay, so send through the Mattermost a message for those of you who have to submit. Send a message to Mohammed Reza and they will put it in the table. Who is submitting? Who needs to submit? 1, 2, 3? 3, okay, so we have to see who's the best spatial modeler out of you 3. It's the least attended spatial prediction competition ever, but never mind, let's see who's the best. It's not about the quantity, it's about quality. Yeah, maybe from the other group, yes. Okay. Well, we need to get the results in, and I because I'm teaching and trying to. I think I was trying to do it here, but somebody asked me a question and then I lost it. But I just have to add it so you can edit. Okay. I'm more or less done with the demo. I don't know did anybody try to follow what I was doing? Yes. So it's pretty straightforward, you know, it's nothing special. You don't load to memory, you first make a tiling system, and then you make a function, then you run that function, you change it, you debug, and then you run it in the whole thing. Yes? SAGA CMD. Yeah, I just heard about this package. I didn't know. So yeah, I don't know how this tiling works. Yeah, no, absolutely. This is not, you know, the ones I show you. This method works for me, and I will tell you. I also use SAGA GIS. I use Grass GIS. I use a lot GDAL. You know, but I will tell you when it gets to like really complicated functions that you want to run on pixels, then you have to make your own function, because R has like enormous possibilities, right? So, and the SAGA GIS doesn't have that. So if you do some process like filter operation, then use SAGA GIS. If you do some process like simple calculus, use SAGA GIS. But when you come to some process where you have to do something complex, then you stop with SAGA GIS. You need to customize it, and then you use Python or R or whatever, and then you build up your own function. And then it's just the question, how do you parallelize that function so it goes very fast? And this works for me very well. So most of my work is using these tiling systems. Every project I have, first I tile, make a function, then I run it. Yes? So that depends on your system. I told you I made that mistakes. I will take a too large tile, and then I start parallelization and I run it to from. So you have to do some estimation, like engineering, you know, like how much water I have, how much cement, you know, things like that. So you have to do that. So I tend to make too big tiles. I don't know, something's in my head, but I always make that mistake, and then I suffocate it. I also, before there was no SSD. You know, when you have SSD, you can make 100,000 tiles, right? So you make 100,000 tiles. But when there was no SSD, I show you this thing. So when I come here to this, if I leave that folder, sorry, this thing. So I'm somewhere this tiling system. And so if I want to enter the folder, look, I just want to enter the folder, nothing special. And it takes about 10 seconds to enter. Why is that? Because it has 10,000 directories. If I want to search something, you know, I have to be very careful. If I just search like T, you know, and now it's suffocating because it's finding so many results. So it's really, it's not simple. So then if you make two small tiles, you can also suffocate. So to search things and find. But when you run it on SSD, this is SSD now, then you can have 100,000 tiles, no problem. And you could search them, copy them, move them, whatever. It will work very fast. SSD is getting close to efficient as RAM. So my advice to you is usually smaller tiles. And now we're looking at using GPU. I checked this out. With GPU, you cannot have large stuff. I mean, it has to be really, really small. So you have to have like a tiles. Let's say if you take an image of Europe, so you have to have a tiles like, you know, 100 by 100 pixels. So I literally create, if I have 30-meter resolution, I create, you know, 100,000 tiles, so 200,000 tiles. But it's for GPU, no problem. You know, if you need to do something complex, it's more efficient in computing. You have more threads. So you could probably, if you put smaller tiles and use GPU, you can compute 10 times faster. And again, a huge difference.